All right, so let's look at the last piece of kind of our calculations. We've looked at calculating our molar masses, we've looked at doing percent compositions, and we very briefly looked at how to do a gram to mole conversion. So what we're going to do today is we're going to use that gram to mole conversion as step one in a three-step process to find the empirical formula of a substance. But first, what exactly is the empirical formula? So when we define this, we define it as a formula that gives you the simplest whole number ratio. Okay, simplest whole number ratio, which means your formula has to be in its lowest reduced form. And what this does is it tells us the relative number of atoms in an element. It may not give us our exact formula, but it tells us, there's 2 carbons for every 1 oxygen or something like that. Okay, and then we have a molecular formula. This is the actual formula of the compound. Okay, so for example, glucose is C6H12O6. That's its actual molecular formula. But if we look at that, C6H12O6, all of those numbers at the bottom can be divided by 6, so they're not actually in their simplest whole number ratio. If we were to actually simplify them, we would get CH2O. That would be our empirical formula, okay? So oftentimes empirical and molecular formulas do not match, but sometimes they do. For example, what's the formula of water? We know it's H2O. That's its actual molecular formula. Well, that formula can't be reduced down any further, which means it's also the empirical formula. We can see here on this slide that we have on the left 3 different molecular formulas. Okay, C6H6, C12H4, Cl4O2, and then C6H16N2. So what I've done on the right is I've showed you, okay, this is what their empirical formulas would look like when we reduce them. So in our first one, both of our subscripts can be divided by 6, so we end up with CH. Here, 12, 4, 4, and 2 can all be divided by 2. So what I did is I simplified them by dividing them by 2. Once one of your elements is down to 1, they can no longer be simplified, okay? Here, 6, 16, and 2 all again can be divided by 2, so we end up with C3H8N. So now, how exactly do we calculate an empirical formula? Because if I give you the molecular and ask you to simplify it, we can definitely do that. But what exactly happens when I just say, hey, my molecule has this much carbon and this much oxygen. What's its formula? How would we do that? Okay, so this is our problem. We have a 0.2015 gram sample of something that has carbon, hydrogen, and oxygen. Okay, and we know this is the breakdown of the mass. We have 0.0806 grams of carbon, 0.01353 grams of hydrogen, and 0.1074 grams of oxygen. So this is what an empirical formula problem would start off as. I would give you the masses of individual elements. You need to use these masses to figure out the actual formula of the substance. So what steps do we follow? Step number 1 is going to be to convert these to moles. So let's do that. Let's convert them to moles. All right, so here's the grams of all 3 of our elements. And so what we're going to do is we're going to convert them to moles. So each one of these needs to be set up as an X-line conversion. So without any other numbers, I'm just going to go ahead and set up their X lines with units. Okay, I want to get rid of grams, so grams is going to go on the bottom in all of them. And remember, we're talking about individual elements here. So I labeled them in the front, so I'm not labeling them in the actual conversion. And we're trying to go to moles. Right, and hopefully you remember from our gram to mole conversion video that when we do a gram to mole conversion, the unit of mole always gets the number 1 with it. Okay, so we automatically fill all of that in. Now, in order to finish this conversion, I need to know essentially the molar mass of each individual element, which means I'm going to look to my periodic table. So for example, we can see here carbon is 12.011. So because I want a molar mass, I'm going to round that to 1 decimal place. So I'm going to use 12.0. Okay. Now I look at my hydrogen on the periodic table. It's 1.0079. So I'm just going to use 1.0. And oxygen is 15.999. So I'm going to use 16.0. Okay. So now I get to do this math. And what I'm going to do is I'm going to use the number of decimal places that my starting number has. This one has 3. this one has 4, and this one has 4. And that's going to tell me how many I want my answer to have. So for carbon, for example, we're going to do 0.0806 times 1 divided by 12. And I'm going to get 0.00. Let's see, I want 3, so 672 moles. So this is moles of carbon. 0.01353 divided by 1. Haha, same answer. 0.01353, but now it's in moles. It's moles of hydrogen. And 0.1074 divided by 16. 0.006713 moles, and that's moles of oxygen. So now I have the moles of all 3 of my compounds, or my elements, sorry. Now that we have carbon, hydrogen, and oxygen in mole form, okay, what we're going to do is we're going to look at the 3 answers and say, okay, which one of these is the smallest? Once we figure out which one is the smallest, we're going to divide all of our answers by the smallest one. All right, so let's look at our numbers. So we have to be really careful that we're really identifying the smallest one. So we look at decimal places. Okay, this for carbon, our number of moles starts in the thousandths place. For hydrogen, it starts in the hundredths. For oxygen, it starts in the thousandths, which means hydrogen's the biggest one. So we're going to ignore that one for now. And now let's look at our other 2. Here we have 0.00672. Here we have 0.00671. So that means that oxygen is technically our smallest one. So what we are going to do is we are going to divide each of our numbers by that smallest number. Okay, so obviously this ends up being 1. Okay, but for these, we actually have to do the math. 6713. Okay, so I'm going to do the math. So 0.00672 divided by 0.0067113. So it's 1, which we could kind of see. And then 0.01353 divided by 0.006713. And I get 2. Okay, so this is actually this set of numbers right here. C equals 1, H equals 2, O equals 1, end up being my answers for step number 2. And now, what does this tell us? Well, this is going to tell us our actual answer of our molecule. Okay, so remember our answers from step number 2 were C equals 1, H equals 2, O equals 1. So this tells us how many of each element we have. So watch me make my formula. C, 1, H, 2, O, 1. So this is my empirical formula. Okay, so let's try this problem as well. An oxide of aluminum is forced by the reaction of 4.151 grams of aluminum with 3.692 grams of oxygen. So let's calculate our empirical formula. Okay, so we are going to do this example problem here, finding the empirical formula. Okay, so what we need to do first, step 1, we need to convert these to moles. Okay, so remember, so you set up your X lines, plug in your units first. So we can cancel out those grams, and we are going to moles. So with molar mass, the number 1 always goes with mole. And now we're going to pull our masses from the periodic table. So for aluminum, my mass says 26.98. So we're going to round that to 27.0. And for oxygen, we know that this rounds to 16.0. So now we're just going to do this math. 4.151 divided by 27. Okay, and we're going to do 1, 2, 3, 4 digits. So we get 0.1537 moles. So that's moles of aluminum. And 3.692 divided by 16. And we get, let's see, 1, 2, 3, 4, 0.2308 moles. Okay, so now we look at these moles and say, which one of these is smaller? Okay, so it's obvious that this one is smaller right here, so we're going to divide both of them by that smaller number. Okay, and let's see what we get. Okay, so this is going to give us 1.2308 divided by 0.1537. It's going to give us 1.5. So when I go to write my formula, right now I have Al1, O 1.5. I obviously can't have that. So what I'm going to do is I know that if I double 1.5, I'm going to get a whole number. So I'm going to multiply this whole thing by 2. So I'm going to end up with Al2, O3, and we know that if we were to actually use our charges from the periodic table to get our empirical formula, that is what we would get.